Thank you, and I'd like to talk about an interesting systems performance issue I worked on earlier this year. An application was moved from one platform to another platform that had containers, and they found that there was a 3x performance improvement. Wow, 3x. Maybe all of Netflix should migrate to this new container platform if we can reduce our server fleet by threefold. It sounded too good to be true, and I've done a lot of work on containers, and I do not expect a 3x win just because you're running under C groups. So I was asked to take a look and find out what was really causing the 3x win. I already knew that the load averages were quite different between the two servers. Server A had a high load average of 90, server B had a load average of 17. Using mpstat, I could see there was a difference where server A was almost completely at CPU saturation. So the idle time was about 2%. Server B had plenty of idle time. So I can see there's only about 25% of CPU utilization. Now remember, server B is running the application faster. The latency for the requests is 3 times smaller. Now when I say a big CPU difference like this, I think a number of things. One thing is that when you are between 0 and 50% CPU utilization, you are not competing with hyperthreads. And so sometimes performance can be better. Once you cross 50% utilization, you then have contention on hyperthreads. So that may be one of the factors that I can drill into deeper. Another factor is these are all shared systems between other tenants, between other Netflix tenants. And when you have a heavily loaded system, there can be more competition for the CPU caches. So that was another clue that I can investigate. For both of those, if I can drill down into an instructions per cycle, for an IPC metric, I can prove or exonerate those theories. So NBStat is just a standard tool. It uses proc statistics. The next tool I tried was PMC Arch. This is a tool I wrote. It's very simple. It summarizes the Intel architectural set of PMCs. PMCs are performance monitoring counters. These are special hardware dedicated counters that are programmable in the CPU for understanding low-level CPU performance. And when I first saw the production server, it was running with an IPC of 0.56. And I was in a meeting room with the application developers. And they hadn't done this cycle type analysis before. In fact, few people, pretty much no one has done this on the cloud before. Because when I joined Netflix, we didn't have PMCs on the cloud. This is something that I've worked with Amazon to get enabled so that we can access PMCs from hypervisor guests. And so when I sat down with the developers, they hadn't used IPC before. And I said, wow, 0.56. I would expect a good application, a well-tuned application, to be running at 1.5. And then I logged into the container host, and sure enough, it was running at 1.5. What's interesting about that is that can explain the 3x performance difference alone. IPC is the instructions per cycle. Your CPUs spend cycles and get instructions retired or completed in return. And so that's a gauge of how fast or how efficient the CPUs are running. So the container host is running with an IPC of 1.5. It's running 3 times faster. Every cycle can process 3 times as many instructions. Remember, all of this is in parallel and out of order execution. A clue as to why the IPC was so different, on the right-hand column, I'm printing out LLC. That's the last level cache or longest latency cache. And on the standard VM, the LLC hit ratio was 30%. On the container host, it was 90%. Again, I would expect this kind of thing because the standard host was running at CPU saturation. And so there was a lot of competition for the CPU caches, whereas on the container host, remember, we had 75% idle. So there's less competition for the CPU caches, so the application gets to use more. And so a consequence of the performance speed up is because the container host is new and we haven't migrated enough tenants there yet. As we move more tenants, the CPU utilization will go up, the last level cache hit ratio may go down, IPC in turn will go down. And these are all connected. There was another difference I don't have on this slide. When I'm looking at LLC hit ratio differences, what are the processor types? And so I looked at the processor types, and they were different. The container host had a larger LLC cache. And so that's another reason why we have a better LLC hit ratio and a higher IPC and a 3x performance improvement. But other things can affect this as well. And I knew that the load averages were really high for the first server. And so I was interested, if the load averages are so high, it was 90 and only had half as many CPUs. What I generally see there is a lot of context switching. And when you context switch between applications, if you're changing address spaces, the processor, depending on the processor, will typically clear the level 1 cache. And that puts more pressure on the later caches. It puts more pressure on the LLC, will drive the LLC hit ratio down. So another factor of the LLC hit ratio being low is higher context switches. And so I used another tool. So this is a hardware-based tool. It's using hardware counters. Now I'm using Perf. I'm using the context switch software event, and I'm using Perf in a special mode where it's doing these counts in kernel. And so it's very efficient. It's not dumping to a text file. And I found on the normal server, the context switch rate was over 2 million. And on the container server, the context switch rate was 1,000. And so certainly with so many context switches, these can flush the level 1 cache, reducing cache performance. And they can also simply not give the application enough time on CPU to warm up the cache. And so I wrote another tool, or used another tool, CPU dist. And this shows the time that the application was spending on CPU when it was scheduled. And on server A, most of the time, the application could only get less than 3 microseconds of CPU time. But on server B with the container, when that application would go on CPU, it would get between 2 and 4 milliseconds, a huge amount more time. So 2 to 4 milliseconds, that's enough time for the caches to warm up better, enough time for the LLC to warm up better with that application's workload, whereas there's too much thrashing on server A. This tool uses BPF, and I'll talk a bit about that later. BPF has been renewed in the kernel, extended BPF, and is now powering a new era of advanced performance analysis tools. And so I found all of these clues. There's all sorts of different reasons for this 3x performance win, but a key one was there was a lot more load on the first server, and the second server was idle. And so it wasn't context switching. The application could use more cache. I thought that was a nice introduction to systems performance because it touches on different types of tools. I'm going to cover systems performance in 45 minutes. This is slides and discussion. I do have books that go through systems performance in a lot more detail. I have a new book coming out, should be next month, BPF Performance Tools, and as part of that, I summarize systems performance as well. Oh. My agenda is really exciting, really large text. I'll switch to PDF if it keeps doing that. I work at Netflix, awesome place to work. We're on Amazon, Linux, Ubuntu, and we have free BSD for our CDN. So the first topic is observability, and I've redrawn my diagrams all over again. I've drawn these things like 3 times. This is a generic diagram of an operating system and hardware. Imagine what tools you use to measure these. Here's my updated diagram. I will put these slides online, and so I'll put all these diagrams online. So I've now been updating where we've got BCC, BPF Trace. I've ditched Netstat. Netstat is now gone. I've got SS and NStat. And so I'll go through a number of these tools. I actually have this diagram printed out on my wall. You think I can remember all these tools? I need this diagram for myself. I sometimes do performance analysis on BSD and other operating systems. And so I have diagrams for the different systems to remind myself. But at Netflix, we don't use tools anyway. We don't SSH onto systems. We use GUIs all the time. We use Atlas, which is our cloud-wide monitoring tool. We used to use Vector. We've now got a new one based on Grafana for doing instance analysis. We sometimes SSH onto a system. That's a last resort. But there is a benefit from learning these command line tools you use over SSH. And one is these tools show the same metrics you see in GUIs. Have you ever used a performance monitoring GUI and you're like, what the heck is this metric? How often are they clearly documented in the GUI? Not that often. Whereas these tools at the command line, tools like VMStat and iostat and SAR and Htop, they've been around for decades. There's so much documentation on how to interpret the output. So it's much easier to pick up, to understand what page faults mean and LLC hit ratios and all of these metrics, to understand what they mean at the command line. And that will help your understanding when you're using the GUIs. And the tools can do more things as well. I'd recommend installing many of these performance analysis tools by default. What you don't want to happen, I've had this happen a number of times, is there is a performance meltdown, and I'm told, Brendan, you have 5 minutes to find the root cause of this performance issue before we use the ELB to switch the load from this ASG to the backup ASG. It's like, all right, 5 minutes. SSH onto the system. Wait, wait, wait. It's like, oh, is it DNS as well? I mean, typically. And by the time I log in a minute later, I find the system is crawling, absolutely crawling. It's like, okay, let's go. iostat, BPF tools, command not found. It's like, okay, like, am I really going to run apt-get update on this system that's absolutely crawling? It's not going to work. By the time apt-get is, by the time I start to see output, they'll have killed the load and switched it to the backup ASG. So yeah, these tools, in fact, I do some dirty tricks to get around this. I made sure we had UUD code installed in all our base AMI. So on every server at Netflix, there is UUD code. Why is that important? This is something I don't recommend doing, but in that situation now, I will go to another machine, I will gzip the binary I want, I'll UU encode it and pipe it to a paste buffer copy tool. Then I go to the production machine, UU decode, and then paste. And so I'm just using my paste buffer to move binaries over really quick. So it's horrible, but it's something that I have to, because like otherwise I have to SCP into the bastions. I know it's going to take a minute to connect. So UU decode, and like there is a way to do you can pipe right into the paste buffer, so it's real quick. So install the tools, don't need to do this all the time. To give you a tour of some of these tools, and some of these you may know pretty well, I use Uptime to look at load averages. They're exposed through many different tools. It's a measure of resource demand. It includes the task uninterruptible state, so it shows all demand types. It's not just CPU demand as it was in other operating systems. I dug into this recently. I did a blog post onto load averages because no one can remember why did Linux add the task uninterruptible state into load averages. If you search for load averages, there's all these blog posts of people saying, yes, it's really confusing because it includes disks. It's like, why? Like, what's the original patch? On Linux, it should be easy. You should be able to do git log -p on the file, and then you go back and you look at the patch that changed it. And so I did it for the load average change, but the trail ran cold. It got to the end of the git history and said, this was imported from another file. Okay, git log the other file. That ran cold. And eventually I'm like, okay, I'm just going to git log all of Linux to a text file and then open it in Vi and do a reverse search. And I found the date predated Linux in GitHub. So this change happened in like Linux 0.9 something. It's like, oh man. So I found some old archives of LKML. It's like, surely I can find it out of these old archives. So I'm going through them and going through them and going through them. And then that trail runs cold. And there is a message from the system administrator saying, I accidentally deleted the LKML archives. And there is no backup. It's like, wow, I didn't realize Linux has a time immemorial event. Like, before the burning of all of the records, no one knows how Linux got to 0.9 999. It's gone. I kept digging, and I found some people have put some old tarballs online from ancient systems. It's a thing, they dig up some deck tape with a tarball and put it online. And I finally found it. I finally found the change. It was from like 26 years ago. And the developer said that he thought the load averages should include disk I/O. Because if you make a change to the system where you move load from CPUs to disks, let's say you put slower disks in a system, now the applications are more blocked on disks than they were CPUs, it would be counterintuitive. The load averages would go down if it's CPU-based, where the load averages should stay the same or higher because the load is queued on disks now. And so he made the change. I emailed him, I found his email address and emailed him, and I got a reply in 1 hour. This is an ancient kernel patch. So finally, so I wrote all the details if you're interested in that archaeology. There is a new technology called PSI, pressure stall information, that splits load averages into CPU memory and I/O so that you can go back to understanding the ingredients. These things are not really averages. They're exponentially damped moving sums, and those are the time constants. They're not that useful. I look at them for 5 seconds. If they're higher than the CPU count, I might have a CPU issue. I'll need to use other tools. 3 of them are useful. Why we have 1, 5, and 15 is because these were created before GUIs were a real thing, or GUIs were very easy to use. Imagine old terminals or teletypes. So it gives you a historical trend without a graph. Top, I'm sure we're all familiar with. Top can straight away tell you who's using top CPU usage, so you can go and investigate. That's a sum. Top can miss short-lived processes. That's why you use Htop, or you can use exec-snoop from BPF. Htop is top with colors. Wow, you read me very well. I wasn't supposed to cast shade on it so clearly. I don't actually like the colors, surprise, because, I mean, what the heck does red mean, vert and res, and this is green? It's the colors. People like colors because it sounds like all this wisdom has been encoded into these thresholds, but it's really, it's just highlighting that these numbers are high and not high or something. I'm not a fan of colors. I've talked about this before. I'll use colors for objective metrics. So if there's a failure, so if a disk has died and there's an error or there's a panic, use traffic lights, use red and green. But a lot of these performance metrics are subjective metrics. And so I tend to not use red and green for that. I'll use other colors or other indicators. What I do like about Htop is it's configurable. And so you can bring in more columns. And dist is similar to Htop in that it will also do colors and to some degree was configurable. Dstat is no longer being updated. There's now a Red Hat version called PCP Dstat. VMStat, virtual memory statistics. The columns I tend to look at, which I've highlighted, I'm looking at free memory, how much is in the buffer cache and the page cache, which is effectively free memory as well. I can also look at system-wide CPU utilization. There's a breakdown of user and system. If I have high system time, I should look at what system calls are happening, what I/O is doing. Tools like this, the first line is the summary since boot, where some of the columns are summary since boot and some are not, which is really confusing. When I document these in my books, I'll tell you which is which. Or you can do some, it's actually pretty obvious because the columns that are the summary since boot kind of change dramatically from the first line to the next, and the ones that aren't don't. So those first 3 columns do not look like the summary since boot, whereas these ones do. The summary since boot gives you a baseline, so you can see how the current activity compares to historic. iostat has been updated recently, so the columns have been changing a little bit. I actually like the iostat -x design, where you've got workload and then resulting performance. And so the workload is the reads, writes, kilobytes, and then the resulting performance, I've got the average weight for reads, average weight for writes, average queue size, and percent utilization. Percent utilization is a little bit difficult to interpret because disks can do things in parallel, so can JBODs. but it just gives you a sense of how busy, during that period of time, how often was something happening on the disks. It's the RA-weight column, or in older versions, just the A-weight column that's most important. That's showing you your read average time in milliseconds. The write average time in milliseconds may or may not matter because the applications can be doing write-back caching, so can the file system. And so even though the disk is showing me 53 milliseconds average wait time, I took this from a recent production system, actually. It's like, actually, that's really high. And I didn't even look at this earlier because I know the application is not blocked on this. This is background flushing. And so I can use other tools, BPF tools, to confirm that. Free, this actually was updated recently as well. So now it's more clear about how much memory is available to applications. Because the free metric itself would drop whenever you booted Linux because Linux would use free memory as a page cache or file system cache. And if your applications needed it, it probably can free it fairly quickly. But that would confuse people because after Linux would boot, the free memory column would go down and people would panic. And there's even a website, linux8myram.com, because it's such a common thing. So now we've got available column, which is more useful than free. Strace. I don't mind Strace in that it's got a lot of translations from syscalls to arguments and mappings. The current implementation slows performance massively. Strace can slow down the target by 100x or 1000x, and that's because it sets breakpoints on syscall entry and return. We've been writing much faster versions using BPF, which I'll get to later. The perf command in Linux is also, Arnaldo's been working on Perf to be an eventual substitute for Strace. So if you run Perf on the latest Linux, it looks like Strace, but it's using per CPU asynchronous ring buffers. It's using BPF for the argument prettifying, and the overhead is much, 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 much lower. I imagine in the future we will switch strace. So when you run user bin strace, it's actually running Perf, you just don't know it, all the same arguments and options. But the performance overhead is now minimal. That'll be great, because then I can stop telling people to stop using strace. You can use strace in a lab environment or test environment. You're debugging something. But at Netflix, if I ran strace on a production Java application, it would be, wow, this is interesting. Look at this out. Oh, the output just stopped. Oh, what's going on? And like within a second, the Hystrix libraries that we use will detect massive latency from that instance and then just redirect traffic to a backup. And so, I mean, it's a good thing from the Netflix environment. It's fault tolerant. I can actually go to a production server and panic it. And it doesn't matter because the requests will go to backup immediately. But if you cause massive overhead on a production server, then it just stops handling traffic pretty quickly. Speaking of massive overhead, I'm also not a fan of TCP dump in that it dumps a lot of things to it can dump all packets to a file. A lot of people have built these post-processing GUIs and whatnot on TCP dump. Like at Netflix, our traffic, we're over 1/3 of the US internet traffic at night. I mean, you can't capture that and post-process it. It's hugely expensive. So again, there can be situations where this is handy. You're debugging things, it's a lab environment. You use filters to try and reduce the overhead, although it's still having to touch every packet. But I try and use BPF wherever possible instead. And there has been a lot of work to make TCP dump go faster. In fact, that was the origin of BPF, was BPF is Berkeley Packet Filter. It was an in-kernel virtual machine that TCP dump uses, so when you type in an expression, it can do the filtering in the fewest possible instructions. So BPF originated to improve the performance of TCP dump. At this point, I would talk about Netstat, but Netstat is no longer the tool to use. It's NBStat from the IP Route 2 package. So IP Route 2 is what the network engineers in Linux are updating as they're changing the code. Remember Netstat and all the like spelling errors and typos and the counter names, and we just deal with it? Well, now we've got NStat, which is actually kind of better. NStat, you can run it before and after an event and look at the delta, like which counters have changed easily. It's got a daemon mode. So if you haven't learned NStat yet, it's the new Netstat replacement. And so it's SS. Slabtop to look into kernel memory. If you have unusual memory growth, that might give you a clue. Speaking of memory, here's another cool tool, PCStat. Shows page cache residency by file. This is used by database administrators, so I can see, are my data files in the page cache or not? This is a way to look inside the page cache. Instead of just talking about the page cache, what's in the page cache? It's pretty awesome. And containers. So if you're on containers, you need to understand how they're using C groups and limits there. And so Docker stats, and there'll be other commands as well. Back to hardware things like my PMC Arch tool, ShowBoost is something I wrote that uses the MSRs, the model-specific registers. These give you status information about a system such as temperatures and configuration. And this is a production system where they had an issue and asked me to take a look. And the CPUs were running at 130 megahertz. And when I saw this, like, I guess I have a bug in ShowBoost because like, surely it can't be 130 megahertz. There must be something wrong with my tool. And then we ran some like CPU benchmarks, and they all ran like 10 times slower than normal. It's like, okay, it's actually running at 130 megahertz. That's amazing. So megahertz fluctuates for all sorts of reasons, including firmware bugs. And so it's a good thing to check. I didn't mention static performance tuning tools at all. These are tools that you can use to examine the state of the system without a workload applied. Richard Elling did a good paper on static performance tuning in the year 2000. And so it's another methodology that's helpful. So I just mentioned lots of tools. So where do you start and where do you stop? Methodologies helps with that. A lot of people don't have a methodology yet, and so I see the streetlight anti-method used where you're using tools that are familiar. I'm using Htop because I always use Htop. Or I'm just tuning things at random. I covered a lot of methodologies in my last book, but a few I want to cover here. Linux performance analysis in 60 seconds. I posted this on the Netflix tech blog. This is the first 10 commands I run when I log into a Linux system. Uptime, demessage, because sometimes the system is sad and the kernel's telling you why. It's in demessage. VMStat, mpstat, pidstat, some SAR things for network I/O, and then Htop for the overview. This is a good way to check the overall health of the system in a hurry. The use method. For the use method, I'll take a diagram of the system that shows the CPU's memory, interconnects, PCI buses. And then for each component, I only want 3 metrics: utilization, saturation, and errors. And some people now have built dashboards that use the use method to make this easy for you to run. And I've published tables showing how to do the use method for different operating systems. What's nice about the use method is it puts you in charge of the questions you're asking of the system. Rather than trying to figure out all of these metrics, you're now saying, these are the 3 that matter for each hardware component. Now I need to go and find those 3. And you'll discover blind spots, things that you hadn't checked before. Workload characterization, this is the methodology I actually find the most performance issues with. It's not about drilling down into the latency and finding some esoteric performance issue. The biggest performance wins are about the load applied is just crazy, and this doesn't make any sense. Workload characterization. So understanding the workload applied, which process IDs, programs, and users. Oh, that benchmark shouldn't be running in production. Someone left it running for weeks. We just didn't have a look. Why? Which code paths and contexts? And flame graphs are great for that. And when developers see it and understand, things are much more inefficient than they thought. So workload characterization. Benchmarking. is another topic from systems performance. And I'll start by saying about 100% of benchmarks are wrong. And that's just the way it is. I don't spend my time refuting bad benchmarks I see on the internet, and other performance engineers I know don't either, because we would get no work done. There's just so many. Benchmarking is, unlike observability, it's an experimental analysis activity, and it's error prone. You can test the wrong target, you can choose the wrong target. I've said before, you benchmark A but actually measure B and conclude you measured C. As an analogy, something I see people do all the time, they're benchmarking a new system but without it configured properly. Imagine you give someone a new car to test drive, and they only drive it in first gear. And they say, oh, I can't buy the car because the top speed was 20 miles an hour. It's a manual. It's like, well, you've got to use the other gears. You've got to change it into second gear and third gear. It's like, well, I didn't do it in my last car, so I'm not going to do it in this car. I'm not going to do it as part of my benchmark. So I see this all the time. People aren't configuring the software and making the wrong conclusions. Micro benchmarks, where you're testing a small component. Macro benchmarks are where you try and simulate the application. And there are kitchen sink benchmarks that run everything. And there's lots of examples of bad benchmarking, like running get-pid in a tight loop, which you can just cache in a library. As another example of explaining why benchmarking is so problematic, I said if your product's chances of winning a benchmark are 50-50, you'll usually lose. And the reason is, when you've got a product and you're convincing someone to migrate, they're not going to run one benchmark. They're going to run 3 or 4, and they expect it to win them all to justify moving. So if you've only got a 50-50 chance, and they roll the dice 3 times or 4 times, there's a greater chance they're not going to win all of them, statistically. The solution for bad benchmarking is active benchmarking, and that's where you have to do root cause analysis while the benchmark runs. For any given benchmark, ask, why isn't it not 10 times faster? This takes time, but you'll figure out all of the problems. Profiling. This is another topic for systems performance. This is a nice example where this description shows where the performance of a new TCP/IP implementation is. 30% handling Ethernet, 10% IP packet processing, 30% TCP processing. And this comes from 1981. And before I did flame graphs, this was kind of problematic to do on modern systems, even though it was done so many years ago. And it's because profiling, say using Perf, the Linux Perf command, can produce so much output that it looks like this. And okay, the answers to I'm 30% Ethernet and 20%, 30% TCP are in here somewhere, but I can't digest it. And so I came up with flame graphs as a visualization for big profiles. And the x-axis is the alphabet, and you just look for the biggest towers, and that's where your time is. And so I can then, if it was 30% TCP, I'd see a TCP tower that was 30% wide. There's lots of different implementations of flame graphs now. In fact, they're in performance monitoring products. Netflix has push-button flame graphs. We do flame graph differentials. And so there's lots of implementations. So if you don't have flame graphs yet, CPU flame graphs. Here's one takeaway from this talk, is implement them because you'll unearth a lot of performance wins. In the slides, I do have instructions for different versions of Linux. In BPF, in older Linux, we had to dump all samples to a file and then post-process, which was CPU and file system expensive. In new Linux, BPF can summarize that in kernel. At Netflix, we've also published Flamescope, which is a performance analysis tool that uses the Perf script output and shows a sub-second offset heat map where each column is 1 second, and you can quickly see variance and perturbations, highlight it, and then you get a flame graph to explain it. And so we're using this internally at Netflix as well. We've open sourced it as well. Perf, apart from profiling, Perf does have access to all the performance monitoring counters, and you can use them for profiling as well. So apart from CPU flame graphs, you might want to do memory stall flame graphs or LLC miss flame graphs. Make sure you've got PEBs so that it's accessing, that's precise event-based sampling, so it's accessing the right instruction pointer offsets. Tracing is advanced Linux performance analysis, although many of the front ends are easy to use. And you've got access to all of these events. So there's trace points, PMC, software events, and I've got dynamic instrumentation. Here's a diagram of the tracing stack. So we like to use BCC and BPF Trace. There's also Trace CMD from Ftrace. BPF enables a new class of performance analysis tools that are custom efficient and production safe. Just to give you some screenshots of what they look like, Ftrace is built into the kernel. It was added by Stephen Restead and others. It's been there for a long time. It's a collection of different capabilities, and it's actually really efficient at some of them. This one is most of them. This one is counting kernel function calls. So I'm saying func count, biostar, those are the kernel calls. And I can do that in production. It's so efficient. Perf, I've already had mentioned in this talk a couple of times, Perf can also use trace points. And so that's events in the kernel, and I can get a log and find out information about them. So here I've traced the block RQ complete trace point. It's giving me information about that event. But BPF is what I've been spending a lot of time at recently, and it lets me do really efficient custom instrumentation. This is ext4 slower, where I'm saying, show me ext4 file system operations that are slower than 1 millisecond, and then it just shows them to me. That's great because your application doesn't talk to disks directly. They talk to the file system. And so having the file system expose where it's slow shows the real application pain in a way the disks do not. And then BCC has all these very easy to use tools. And then BPF Trace is a new front end where you can do these custom one-liners and short scripts very easily. So here I'm summarizing the RWBS, which is the type field of block I/O. So I can see I had 86,000 reads and 2 synchronous writes. Here I'm doing a histogram of the size of the block I/O by process name. Amazing stuff. So BPF Trace, check it out. I've written a lot of BPF Trace tools in my upcoming book, and there's a diagram of all the tools you have access to now. So again, this is all online, so you can check it out, and it's all open source, so you can get them installed on your systems. Off-CPU analysis is something I just wanted to mention because it's something BPF is making possible because it's efficient. So instead of looking at CPU time, I can look at blocked time as a flame graph. The last thing I've got is I've just copied and pasted the standard tuning we use at Netflix. Some of you might think this is the most exciting part of the talk. I don't, because I worry you'll just copy and paste this blindly into your servers. So I don't want to spend too much time on it. This is like raiding someone's medicine cabinet. This made sense at a particular point in time, but it may not make sense. If I find this 5 years from now in your production servers, it may not make sense. You may need to update it. So these slides will be online, and something recently we've changed. We're using the Kyber block I/O scheduler now. We're now using QDisks, which is the networking queuing disciplines, which can improve performance. And there's lots and lots and lots of different QDisks for improving network I/O and doing all sorts of classification and things. So check them out if you haven't looked at QDisks yet. A lot of them are from Eric Dumazet at Google. And also from Google, BBR, TCP congestion control. We're now using that at Netflix as well. So there are 3 takeaways I'll give you from this talk. For your office wall, you can print out the Linux performance analysis in 60 seconds checklist. The diagrams I've got of observability tools and flame graphs. If you don't have flame graphs, who has flame graphs working right now at work? So maybe a quarter of the people. I need to see more hands in the future. They solve so many performance issues at Netflix. They're amazing. So do get them automated. In these slides, I've got links. And now we have 5 minutes for questions.